Good morning, everyone. My name is Balal Yousaf, and I'm representing the Department of Technologies and Installation for Waste Management at Silesian University of Technology. It's a pleasure to welcome you to this discussion on the future of circular economy, challenges, and opportunities. As we explore the shift towards a circular economy where resources are reused and recycled rather than discarded, we will discuss how different sectors are driving this transformation. To start, I will share some insight in my presentation entitled Bioenergy Innovation, Driving the Circular Economy Forward, focusing on the latest advancement in bioenergy that is shaping this field. I will start with my presentation and then we will move on to our esteemed speakers. Thank you so much for your attention. Let's begin.
Good morning, everyone. I'm honored to be here with you today at the European City of Science, Katowice 2024. My name is Balal Yousaf, and I'm working as a professor in the Department of Technologies and Installation for Waste Management at the Silesian University of Technology. Today, we will be discussing an important and timely topic: bioenergy innovations driving the circular economy forward. This topic lies at the intersection of sustainable energy production and resource efficiency, which are very crucial for our future. So let's begin with the basics about the bioenergy. Simply, we can say it's a form of energy that we generate from biological material, which we commonly refer as biomass and food scrap. This can include anything from plant, wood, and agricultural waste to organic waste from our homes and industries, such as food scraps and sludge. These materials are rich in energy because they store energy from sun through the process of photosynthesis, and by converting biomass into energy, whether it's in the form of heat, electricity, or fuel, we can utilize this natural energy for our daily need. For instance, we burn wood in a fireplace, that a very basic form of bioenergy, but today technology allows us to process biomass in much more efficient and sophisticated way to produce renewable energy on a larger scale. So why is bioenergy so important in today's world? First and foremost, bioenergy play a critical role in reducing our reliance on fossil fuel, which are not only finite but also a major contributor to climate change. So by replacing fossil fuel with bioenergy, we can significantly cut down on greenhouse gases emission. For example, using biofuel in place of conventional gasoline can reduce carbon emission from transportation up to 90%. Bioenergy also contribute to energy security because biomass can be sourced locally. It reduces our dependence on imported fuels and also helps stabilize energy supplies. So this is particularly important in regions where energy resources are very limited. And additionally, bioenergy is renewable. Unlike fossil fuels, bioenergy can be replenished relatively quickly, making it a sustainable option for future. Now that we have basic understanding of bioenergy, let's explore how it fits into the broader concept of circular economy. The circular economy is an important economic model that contrasts sharply with traditional linear economy. In linear economy, we normally follow a take, make, and dispose approach. It means that resources are extracted, used to make product, and then discarded as waste. This model is unsustainable in the long run because it leads to the depletion of natural resources and the accumulation of waste material. So alternatively, the circular economy aims to keep resources in use for as long as possible. It's based on three key principles: reducing waste and pollution, keeping products and material in use, and regenerating natural system. By recycling, reusing, and regenerating, we can minimize waste and make the most out of the resources we have. So it is a perfect example of this model in action because it turns waste into value-added resources like energy and other materials. We can say that bioenergy is a cornerstone of the circular economy because it helps close the loop of resource usage. For instance, in the agricultural sector, crop residues like straw or husk, which would otherwise go to waste stream, can be converted into bioenergy. So this not only provide a renewable sources of energy, but also reduce the amount of waste that ends up in landfill. So let's take the example of sugarcane processing. After extracting sugar from sugarcane, what remains is called bagasse, a fibrous residues. So instead of discarding bagasse, it can be burned in a cogeneration plant to produce electricity and steams, which can then be used to power the sugar mill itself. So this process is an excellent demonstration of circular economy, where every part of resource is utilized and waste is minimized. To give a concrete example, let's look at a successful bioenergy project that explains the principle of circular economy. In Denmark, there's a project called Kalundborg Symbiosis. This industrial ecosystem involves several companies that share resources and energy in closed-loop system. One key element of this symbiosis is a bioenergy plant that convert waste product from local industries such as straw and wood chips into energy. And the heat and electricity generated are then supplied to nearby factories, residential area, and even a fish farm. This byproduct of the bioenergy process, such as ash and the organic residues, are further used as a fertilizer in agricultural land. So this project not only reduce waste and emissions, but also create synergy between different industries, showing how bioenergy can drive a circular economy. Technological innovation has played a significant role in advancing biomass conversion process, making them more efficient and sustainable. For example, traditional biomass burning methods like using wood for heating are relatively inefficient and can produce harmful emissions. However, modern technologies such as pyrolysis and gasification has revolutionized the way we convert biomass into energy. So in the form of pyrolysis, it involves heating biomass in the absence of oxygen, producing a mixture of liquid bio-oil, gases, and solid biochar. This process can be fine-tuned to maximize the production of bio-oil, which can be used as a renewable fuel. And on the other hand, gasification converts biomass into synthetic gas called syngas, which can be used to generate electricity or as a building block for producing chemicals and fuels. These advancements not only improve the energy yield from biomass, but also reduce the environmental impact by lowering the carbon and the pollutant emission into the atmosphere. So biofuel has evolved significantly over the years. First generation biofuel have been widely used, especially in the transportation sector. However, they have faced criticism for competing with food production and having a relatively modest environmental impact. This led to the development of second generation biofuel, which are produced from non-food biomass such as agricultural waste, wood chips, and grasses. So these fuels offer a better environmental profile because they don't compete with food crop and can be made from a waste material. So an example is cellulosic ethanol, which is produced from cellulose in plant cell wall and can be used as a renewable transportation fuel. And at last, there is a third generation fuel, and it represents the latest innovation, and they are derived from advanced sources such as algae, because algae has several advantages. They can grow in a variety of environment, including non-arable land, required minimum water, and have high yield. So algae-based biofuel have the potential to be produced at a larger scale without the environmental drawbacks or ideal biofuels. Current research is focused on making algal biofuel production more cost-effective, which could be a game changer for the industry. Biogas production has also seen exciting development. Traditionally, biogas is produced through anaerobic digestion, where microorganisms break down organic matter in the absence of oxygen. The result is biogas, which is primarily composed of methane and carbon dioxide. While this process has been used for many years, recently innovations have significant improvement its efficiency and application. For example, new technologies now allow upgradation of biogas to methane by removing impurities. So biomethane has the same properties as natural gas, making it more suitable for use in existing natural gas pipeline and as a fuel for vehicles. So there is an example in Germany. Biomethane is increasingly being used to power buses and trucks, providing renewable alternatives to diesel. Another innovation is the development of small-scale digester that can be used by farmer or communities to produce biogas from agricultural waste, providing a decentralized and sustainable energy source. As I mentioned previously, algae is one of the most promising source of bioenergy, often referred as the green gold of the future. Unlike a traditional crop, algae can grow rapidly and can be cultivated in environments that are unsuitable for the food production, such as saline water or desert area. So this makes algae a highly sustainable source of bioenergy. It can be processed to produce a variety of bioenergy products. The most well-known is algal biofuel, which can be refined into biodiesel or jet fuel. In addition to biofuel, algae can also use to generate electricity in algal biomass power plant or to produce bio-based products such as bioplastics. It has the added benefit of the absorption of carbon dioxide during growth, making it a carbon neutral or even carbon negative energy source. So companies and research institutions around the world are actively exploring ways to commercialize algae-based bioenergy, and we are likely to see significant advancement in this field in the coming years. Recently, decentralized bioenergy systems are gaining popularity as they offer a number of advantages, particularly in rural and remote areas. Unlike centralized energy system where energy is produced at large facility and then transmitted over long distance, decentralized systems generate energy locally and reduce transmission losses and increase energy security by making communities less dependent on external energy sources. And one of the example of a decentralized bioenergy system is the use of microgrids power by the local biomass and biogas. These systems not only provide a reliable source of energy, but also create local jobs and support community development. This system can also play a key role in disaster resilience, ensuring that communities have access to energy even when centralized systems fail. Well, waste to energy is a powerful concept that turns a problem, which is waste, into a solution in the form of energy. Advances in waste to energy technologies have made it possible to convert various types of waste, including agricultural residues, industrial waste, and municipal solid waste into valuable energy product. One of the most promising technology is gasification, which involve heating waste materials at high temperature in the presence of controlled amount of oxygen. This process uh, produce syngas, which can be used to generate the electricity or as a feedstock for producing chemicals and fuels. Another technology is anaerobic digestion, which we discussed earlier and is particularly effective for producing organic waste like food scraps and animal manures. A successful example of waste to energy innovation can be found in Sweden, where waste to energy plants have become an integral part of the country's energy system. Sweden now import waste from other countries to fuel its waste to energy plants, reducing landfill use and generating heat and electricity for its cities. This is a clear example of how waste to energy technologies can supply and support the circular economy. The economic impact of bioenergy is substantial, particularly in terms of job creation and economic growth. The bioenergy sector creates jobs across the entire values chain, from farming and biomass collection to processing, distribution, and research. These jobs are often in rural areas where employment opportunities can be limited, making bioenergy a valuable driver of rural development. For example, in Brazil, the bioethanol industry has created hundreds of thousands of jobs, from sugarcane farming to ethanol production and distribution. This industry has not only provided employment but also contributed to Brazilian economy and energy security. In addition to job creation, bioenergy can lead to cost saving by reducing the need for waste disposal and providing a local source of energy. For a community that rely on imported fuel, bioenergy can offer a more affordable and stable energy supply. The economic benefit of bioenergy make it an attractive option for both developed and developing countries. Bioenergy also offers a range of environmental benefits that make it a key component of our strategy to combat climate change and promote sustainability. One of the most significant benefits is the reduction of greenhouse gases emission. When bioenergy is produced sustainably, it can result in much lower emission compared to fossil fuel. For example, using biofuel instead of gasoline can reduce carbon dioxide emission by up to 90%, and this is the proved fact. Bioenergy also helps reduce waste as it allows us to convert organic waste materials into value-added or valuable energy. This reduces the need for landfill, which are a major source of methane emission, and furthermore, bioenergy promotes sustainable land use by encouraging the use of marginal lands for biomass production and reducing the pressure on forest and other ecosystem. However, it's important to ensure that bioenergy is produced in a way that does not harm the environment. This means carefully managing land use, avoiding deforestation, and ensuring that water resources that are used sustainably. When done right, bioenergy can be a powerful tool for environmental protection and sustainability. While bioenergy has many benefits, it also comes with challenges and risks that need to be carefully managed. One of the main environmental concerns is the potential for deforestation and loss of biodiversity if biomass production is not managed sustainably. Another challenge is water use. Bioenergy crop can be water intensive, and in region where water is scarce, this could lead to competition with other water need such as food production and drinking water. Economically, the high initial investment required for bioenergy infrastructure can be a barrier, particularly in developing countries. Global policies play a crucial role in supporting the development and adoption of bioenergy. The Paris Agreement, for instance, is a landmark international accord that aims to limit global warming to well below 2 degrees Celsius. Achieving this goal required a significant reduction in greenhouse gases emission, and bioenergy is an essential part of this solution. Organizations like International Renewable Energy Agency are also promoting bioenergy as a key component of the global renewable energy mix. At the national level, many countries have implemented policies to support bioenergy. For example, United States has a renewable fuel standards that mandate the use of biofuel in transportation, while the European Union has set ambitious targets for renewable energy uses, including bioenergy. So these policies are essential for driving the growth of bioenergy and ensuring that it contributes effectively to our climate and energy goal. Different regions and countries have taken unique approaches to bioenergy, often reflecting their local resources, needs, and priorities. And Brazil is a global leader in bioethanol production. On the other hand, in the European Union, bioenergy is a central part of a region's renewable energy strategy. The United European Union Energy Directive sets binding target for renewable energy use, including bioenergy, and encourages the use of sustainable biofuel in transportation. As a result, countries like Sweden and Finland have already developed advanced bioenergy system, including waste to energy plant and district heating network powered by biomass. Let's discuss about a case study from Europe where bioenergy has become a key component of the energy system. In Sweden, waste to energy plants have been integrated into the country's circular economy, providing a sustainable solution to both waste management and energy production. This approach not only reduces the city's reliance on fossil fuel, but also minimize waste and support the local economy. This plant is a shining example of how bioenergy can be integrated into a circular economy, creating a sustainable and resilient energy system. Turning our attention to North America, we see a strong focus of biofuel, particularly in the United States and Canada. The US has invested heavily in bioethanol production, with the renewable fuel standards driving the use of ethanol in gasoline. Today, ethanol accounts for about 10% of the US gasoline supply, helping to reduce carbon emission and support agricultural sector. In developing countries, bioenergy play a crucial role in addressing energy poverty and promoting sustainable development. For example, in India, biogas program has been widely implemented in rural areas, promoting clean cooking to millions of households. Similarly, in sub-Saharan Africa, biomass energy is a vital source of energy for many communities, particularly in rural areas. Projects like small-scale biogas plant are being installed in schools and farms, providing renewable energy for cooking, lighting, and electricity generation. As the world moves towards decarbonization, bioenergy will play a crucial role in achieving net zero emission. Unlike other renewable bioenergy, can provide a stable and continuous source of energy, making it an essential complement to intermittent source like wind and solar. It also has the unique ability to decarbonize sectors that are difficult to electrify, such as aviation, shipping, and heavy industry. To summarize, bioenergy is a vital component of the circular economy, helping to turn waste into energy and providing a renewable and sustainable source of power. We have explored the different types of bioenergy from biomass and biofuel to biogas and see how technologies innovations are making these processes more efficient and environmental friendly. We have also discussed the economic and environmental benefits of bioenergy, including job creation, reduce greenhouse gases emission, and improve resource efficiency. As we look to future, continued research, innovation, and collaboration will be essential for unlocking the full potential of bioenergy. So, by integrating bioenergy into our existing energy system and the circular economy, we can build a more sustainable and resilient future. As we have discussed, the challenges facing bioenergy are significant, from environmental concerns like deforestation and water use to economic barriers such as high initial investment cost. However, these challenges also present opportunities for innovation and collaboration. By investing in sustainable practices, we can mitigate the environmental risks associated with bioenergy and ensure that it contributes positively to our climate goal. For example, by using waste and non-food biomass as feedstock, we can reduce competition with food production and lower the environmental impact of bioenergy. Economically, the bioenergy sector offers opportunities for job creation, particularly in rural areas, and for diversifying energy sources, which can enhance energy security. With the right policies and investment, we can overcome the barrier to bioenergy adoption and unlock its potential as a driver of the circular economy. At last, I encourage policymakers, industry leader, researcher, and student to take an active role in the development and adoption of bioenergy, whether through policy support, technological innovation, or community engagement. Your contribution can make a significant impact. Thank you so much for your attention, and I look forward to your questions and the discussion to follow.
Thank you all for your attention during my presentation on bioenergy innovations. Now it's my pleasure to invite our next speaker, Dr. Liu Ruijia, Associate Researcher at University of Science and Technology of China. She will present on waste to wealth, the resource role of bioenergy in waste management, sharing how bioenergy can transform waste into value-added product. Dr. Liu, the floor is yours.
Good afternoon, everyone. I'm Ruijia Liu, a research associate in environmental science and engineering from University of Science and Technology of China. It is a great honor for me to address my work related to the topic Waste to Wealth, the role of bioenergy in waste management with you. To begin with, I'd like to talk about what is waste. Waste is a product or substance which is no longer suited for its intended use. Can be divided into three types, including liquid, solid, and gaseous waste. Waste materials from human activities can take a long time to decompose. And as can be seen, solid waste can further divided into mining, agricultural, industrial, household, construction waste, and wastewater treatment. Large amounts of those wastes have been generated. From this figure, we can see that global solid waste is increasingly generated. In 2023, 2.3 billion tons of solid waste were generated, and the amount is projected to reach 3.4 in 2050. According to the World Bank data, solid wastes are primarily being treated by landfill, open dump, and incineration, while recycling and recovery only account for less than 50%. Those waste treatments can cause environmental pollution, greenhouse gas emission, and also waste of sources. Now, we are in an urgent need of solid waste management. The EU waste management hierarchy includes prevention, preparing for reuse, recycling, and other recovery and disposal. According to this, different types of solid waste should be treated with specific methods. Solid waste usually consisted of mostly food and grain, paper and cardboard, plastic, gas, metal, rubber and leather, wood, and others, among which paper, glass, metal cans, plastic, and cartons are recyclable, while others like e-waste are not recyclable and can be refurbished and recovered with metals. Industrial waste such as mining tailings and coal combustion ashes can be recovered with metals or used in construction material. Hazardous wastes are treated separately, and biomass waste such as food, straw, and sewage sludge account for the largest amounts, can be recovered with energy, substance, and carbon materials. Meanwhile, the worldwide rapid development has caused energy crunch, environmental pollution, global warming, which means that we are in an urgent demand for renewable energy sources. And among all the renewable energies, biomass is widely distributed, not restricted by natural conditions, stable in yields and prices, and is the only renewable carbon source. The abundant biomass sources on Earth is of great prospect. Annual biomass yield from plant is around 1,440 to 1,700 billion tons. Besides, there are other considerable wastes, such as manure and sewage sludge. Specifically, biomass involves woody agricultural biomass, plant-related industrial residues, aqueous biomass, manure, and sewage sludge. And those biomass can be converted into bioenergy, including solid fuel, heat, syngas, flue gas, bio-oil, biochar, and bioethanol using physical, thermochemical, and biochemical techniques. Among all the techniques, the physical is usually of low energy conversion efficiencies. For the thermochemical techniques, combustion is inadequate for conversion and can cause pollution. Gasification needs higher energy input and high pressure and catalysts for hydrolysis, longer duration and limited input biomass types for biochemical techniques. For pyrolysis, it is flexible in time and raw materials, and also beneficial for adequate multi-conversion of biomass. Then, what is biomass pyrolysis? Those biomass feedstock are put into the thermal conversion reactor under 300 to 700 degrees centigrade without oxygen. During the process, we can get biogas, bioil, and finally solid biochar. While further into the inner molecular conversion process, we can explain from the thermal degradation and interaction of biomass, main ingredients, cellulose, hemicellulose, and lignin. During pyrolysis, dehydration occurs at below 200 degrees centigrade. At between 200 and 500 degrees centigrade, primary pyrolysis, including fragmentation and shrinkage, occur with the formation of primary gas and oil. Then secondary charring of the oil generates primary tar. When the temperature increases to higher than 500 degrees centigrade, secondary cracking of oil with char devolatilization to generate gas, oil, and biochar. With the generation of those pyrolytic products, biomass pyrolysis is significant for waste mitigation. Biochar can be used for carbon sequestration, soil enrichment, environmental remediation. Besides, bioil, syngas, and biochar are also renewable clean energy. However, the properties of the pyrolytic products and the resulting application benefits can be influenced by feedstock types, pretreatment methods, pyrolysis operators, and conditions such as temperature, atmosphere, catalyst, heating rate, duration, and pressure. It means that the properties of pyrolytic products are not always stable. We need to understand the pyrolysis behaviors. Current research on this area can be restricted by the thresholds of influencing factors and corresponding mechanisms, as well as the detailed reaction occurred during pyrolysis and the fate of intermediates. Many scholars have made comprehensive progress in biomass pyrolysis chemistry, but this is still limited. We still have difficulties in precise regulation of pyrolysis process, efficient utilization of biomass, and the consequent scale-up with target pyrolytic products. Thus, it is crucial to go deep into the pyrolysis process chemistry. Upon this, I would like to introduce some of my research work on this topic, pyrolysis mechanisms and kinetics for biomass at a molecular level. The pyrolysis process was investigated with peanut shell using in situ pyrolysis techniques, TGFTIR mouse for volatile monitoring, and in situ FTIR for the real-time evolution of solid matrix. According to the TG-DTG curves of PS, we selected 31 sampling points and at different temperatures for in situ analysis and obtained 31 spectra. Afterwards, each of the FTIR spectrums was divided with 4 sections according to the actual situation. There are hydroxyl and aromatic stretching at 3,000 to 3,750 wave number, and aliphatic carbon hydrogen stretching at 2,800 to 3,000 wave number, and 1,550 to 1,800 wave number for carbonyl and aromatic skeleton vibration, and also 1,000 to 1,550 wave number for aromatic ring vibration and carbon-oxygen single bond stretching. This section of one spectrum was deconvoluted individually via PeakFit software. After that, the peak areas of 5 functional groups were obtained for further analysis. Deep into the in situ pyrolysis result for peanut shell from the 3D TGFTR spectra and cumulative adsorption curve, we can see that the total volatile content reached the peak at approximate 410 degrees centigrade. Referring to the Beer-Lambert law, the adsorption curve of each volatile could indicate the relative product concentrations. Therefore, the TGFTIR profiles of individual gas products and functional groups implied that their concentration were in this sequence. Coupled with TGFTIR, mass was applied to detect the fragments with mass-charge ratio range from 16 to 252, and these are the major identified compounds. A 3D mass spectra and TIC curve showed the peak temperature for most released compounds were at 434 degrees centigrade. More specifically, at a temperature below 200 degrees centigrade, only the 4 gases were generated. At 410 to 433 degrees centigrade, most compounds reached the maximum due to the timely pyrolysis of lignin and previous degradation of hemicellulose and cellulose. At 620 to 780 degrees centigrade, most compounds reached the plateau, and finally, at the temperature higher than 700 degrees centigrade, the amounts and varieties of polyaromatic hydrocarbons increased since the side chain decarbonization and decarboxylation at a high temperature. The in situ evolution of functional groups in the solid chain matrix were presented in the form of peak areas. This is the integral peak areas of the detailed hidden peaks in each deconvoluted section. The upper left shows that aliphatic hydrocarbons is mainly composed of carbon, hydrogen, and carbon, hydrogen-2 of carbon-6 methylene in cellulose, as well as carbon, hydrogen in cellulose structure and lignin side chains. In particular, hydroxyl, carbonyl, and carbon-oxygen bonds changed before the aromatic carbon skeleton. The decrease in the peak area of fused aromatics at 1,514 wave number during 210 to 500 degrees centigrade demonstrated that the single benzene was reconstructed and polycondensed into complicated fused structure with weak FTIR signal. The carboxyl groups include amide and unsaturated ketones, acids, and olefin. Unconjugated carboxyl, aldehyde, and aliphatic ketone. The increase in hydroxyl groups during the pyrolysis of penetrate at 13 to 216 degrees centigrade was mainly induced by the dehydration of hydroxyls, degradation of glucopyranose rings in cellulose. The further decrease was attributed to the decarbonization of fragments into pyrolytic intermediates and gases like carbon dioxide and carbon monoxide during aromatization, as well as the auto condensation of carboxyl functionalities to produce macromolecular biochar matrix. Then, carbon-oxygen groups involved those 5 derived from alcohols aliphatic ester bound at 1,160 wave number phenols and is a linkage. The decrease in total carbon-oxygen bonds was attributed to the cleavage of glycosidic bonds, pyrene ring opening, and fragmentation. Besides, rapid onset in carbon-oxygen at 1,030 and 1,110 wave number suggests that aliphatic carbon-oxygen carbon and carbon hydroxide were weaker than other carbon-oxygen groups. Furthermore, hydroxyl, carboxyl, and carbon-oxygen groups eliminated at 500 degrees centigrade. This means that most oxygen-containing functional groups were fractionated into liquids, including aldehydes and ketones, by 500 degrees centigrade, with char formed. For thermokinetic analysis of the 5 functional groups in the figure, those functional groups were separated, fitted. The variation of total hydroxyl and hydrogen-bonded hydroxyl stretching were divided into 2 stages, while the free hydroxyl stretching showed an overall decreasing trend but fluctuated dramatically with 4 stages, and for aliphatic hydrocarbons, there were those decline stages. Aromatic and carboxyl groups also showed 3 stages, but with first 2 increasing and the 3rd stage decreasing. And the variation of total carbon-oxygen was divided into 4 stages. Those different pyrolysis behaviors suggest that they have different pyrolysis mechanisms. Based on the above deconvoluted peak areas and curve fitting results, we use Coates red fin method to analyze the pyrolysis kinetics for hydroxide. Hydroxide at 301,000 to 366,000 when number. Aliphatic growth, carboxyl and carbon oxygen to obtain kinetic parameters including activation energy E, pre-exponential factor A, and mechanisms. There is no pyrolysis kinetic results of aromatics because it is unable to confirm their final quantities. According to the result in Table 1, hydroxyl growth possessed the small E and A values indicated that dehydration is beneficial to biomass degradation, while carbon-oxygen growth at 300 to 500 degrees centigrade possessed high E and A values. It means that the degradation reactions are very complicated. Meanwhile, the pyrolysis mechanism models at 20 to 380 were primarily diffusion, influenced by heat and gas mass transfer from biomass particles. Along with the temperature increase, the pyrolysis mechanism models were the combination of diffusion model and second or third order chemical reaction model. It is because lignin degradation and charring reaction occurs at the high temperatures. We have the following findings. The conclusion, the TGFTIR mass spectra indicated the concentration of the volatiles within this sequence and reaching the maximum at approximately 410 to 433 degrees centigrade. And the multi-stage pyrolysis kinetics of the main functional groups in the solid matrix during penetrable pyrolysis at 20 to 500 degrees centigrade was revealed for the first time. And the pyrolysis mechanisms and models for the functional groups in the Char matrix was a combination of diffusion model and second or third order chemical reaction model. And this is my overall presentation on the topic waste to wealth. Thank you for your attention. If you have any questions, you can just write below.
Thank you, Dr. Liu Ruijia, for such a nice presentation on transforming waste into value-added resources through thermochemical conversion process. Our next presenter is Dr. Majad Mansoor, an assistant professor at the Institute of Intelligent Manufacturing Technology, Shenzhen Polytechnic University, China. Dr. Mansoor will explain technological, economical, and environmental benefits of circular economy practices in European Union wind energy. Dr. Mansoor, please take the stage.
Welcome everyone. My name is Assistant Professor Majad Mansoor. Currently, I'm affiliated with at Shenzhen Polytechnic University. My area of research is optimization and renewable energy and green technologies. The agenda is structured to provide a comprehensive overview of the current state of the art and future perspectives of wind energy within the European Union. We will emphasize the importance of AI in enhancing the efficiency and reliability and sustainability aspects of wind energy technologies. The topic of our today's presentation, circular economy of wind power in the EU. Wind energy is the leading renewable energy technology. It is a testament of the collaborative efforts of researchers, policymakers, and industry leaders to harness full potential of wind energy within the European Union. We will explore how artificial intelligence applications in wind energy technology can be used to drive efficiency, reliability, and sustainability in the circular economy of the wind energy sector. Our aim today is to address the impact of artificial intelligence on improvising the circular economy of wind turbine. In the first half of presentation, we will outline the significance of wind energy in the EU's transition to a sustainable and low carbon economy, how it applies to the wind energy sector, and underscore the EU's commitment to renewable energy sources as part of its broader climate action strategy. The second part will elaborate the impacts of onshore and offshore wind turbines, discussing the unique challenges and opportunities. At the end, we will highlight the key improvement sectors. We will show how deep learning models, forecasting, and inspection of wind turbines adds to the long-term circular economy. The conclusion and future directions section wraps up our presentation. Renewable energy progress in the European Union is driven by the European Commission 2023 revision of the Renewable Energy Directives, which raises the EU's binding renewable energy target for 2030 to be at least 42.5%. That is up from the previous target of 32%. This policy shall be effective since November 2023 across all EU countries. This directive aligns with broader climate objectives, including reducing greenhouse gases emissions by at least 55% by 2030 and achieving climate neutrality by 2050. Additionally, the Energy 2020 strategy exceeds its goal, which is very good, with the EU's achieving 22.1% of share coming from the renewable energy sectors, that is surpassing its goal by 2%. The map here shows the extent of wind power turbines operational at EU countries. The map only shows 5 megawatt or above turbines currently of 17,000 such installations, and roughly 8,000 are in pipeline. To have a deeper look into the penetration of wind energy in EU, we can have a regional look at it. The European Union can be divided into 4 subregions. In 2018, wind energy generated enough electricity to meet 14% of EU's electricity demand. Denmark had the highest share of wind, almost 41% in Europe, followed by Ireland 28% and Portugal 24%. Germany and Spain follow with 21% and 19% respectively. Out of EU's total electricity consumption of 2,645 terawatt-hour in 2018, onshore and offshore contributed 3,009 terawatt-hours, that is 12%, and offshore wind contributed to 2%, that is 53 terawatt-hour, bringing the total consumption of around 14%. that is 632 terawatt hour. The energy comes from a total onshore wind capacity of 160 gigawatt and total offshore wind capacity of 18.5 gigawatt, with an average capacity factor of 24% across these regions. The graph shows us the wind power per capita in 10 EU countries. A 2009 European Environmental Agency report stated that Europe's onshore and offshore wind energy potential confirms with energy could power Europe many times over. The report highlights wind power potential in 2020 as 3 times the demand of the EU's electricity. Europe expects electricity demand rising to a factor of 7 by 2030. An EWEA report overviewing 2009 data estimated that 230 gigawatt of wind capacity will be installed in Europe by 2020, consisting of 119 gigawatt onshore and 40 gigawatt or offshore. This would produce 14 to 17% of the EU's electricity, avoiding 333 million tons of CO2 per year and saving Europe's $28 billion in fuel cost. Norway has a remarkable offshore potential. According to IEA, wind energy market size is expected to reach 6 gigawatt in 2024 and grow at a cumulative average of 7.73% to reach 8.77 gigawatt by 2029. The drive for electric transportation requires further utilization of wind energy for cost-effective mode of transportation. To meet these goals, the Norwegian government aims to install offshore wind power with total capacity of 30 gigawatt by 2040. These are the very, I would say, strong goals to achieve, and as this puts an example in the EU countries, how the EU countries are very much integrated and enthusiastic about the wind energy, and how in the long term the policies are favoring the wind energy, and there is a huge need for the studies in the perspective of circular economy on these technologies. Within a circular economy framework, high power wind turbines offer significant potential for sustainable energy production, but also present challenges related to material usage, manufacturing impact, and end-of-life management. We will focus on reducing environmental impacts during manufacturing, enhancing efficiency to shorten energy payback periods, and improving recycling process are critical steps towards integrating wind turbines into circular economy model. The actual comparison and efficiency analysis of high-power wind turbines, particularly focusing on their role within circular economy, involves considering various factors such as environmental impact, energy payback time, and the potential for recycling, reuse of materials at the end of their life cycle. The literature generally offers insights primarily into the life cycle assessment, or LCA, of wind turbines, but these principles can be extrapolated to understand the implications of large turbines within circular economy framework. The graph here shows the new wind power installation in EU in year 2023. The capacity factors for new onshore wind farms built in Europe in 23 range between 30 and 45%, and for offshore they were around 50%. The average power of new onshore wind turbine installed in 23 was 4.5 megawatt, representing an increase from 4.1 megawatt in 2022. For offshore, the average power was 9.7 megawatt compared to 8 megawatt in 2022. Large turbine means more waste material is available for repurposing, and extending operational life becomes cost-effective choice for policymakers. Wind turbines are up to 90% recyclable. Due to financial restraints, recycling should be replaced by repair and hence increase the longevity of the existing fleet. The scale of wind energy is so broad that it mandates modern technologies to assist in operations. For example, the UAVs, or unmanned aerial vehicles, or drones, revolutionized the wind turbine inspection by offering advantages in safety, cost savings, and efficiency. The ability of UAVs to closely examine the turbine components without requiring the turbine to stop operation significantly enhances operational flexibility and minimizes downtime, thus maximizing energy production. Drones quickly inspect as compared to the humans, and their inspection times and single operator requirements are very simple logistically, and they are able to reduce the cost of the inspection up to 70%. UAV deployment is potentially hazardous environment ensures the safety of human inspectors, making drone inspections a safer option. The dual sensor capabilities of drones that enable both visual and thermal data collection provide the comprehensive insights into the turbine's condition. This adaptability highlights the crucial role of UAV-based inspection in the maintenance and longevity of the wind turbines. In context of circular economy, prevention, reuse, repurposing, recycling, recovery, and disposal uh, of materials are of paramount importance in the context of any technology. The principle of prevention is paramount, especially when it comes to the maintenance and longevity of the wind turbines. Unlike traditional linear economic models that often prioritize repair, replacement, or disposal after failure, a circular approach emphasizes prevention, uh, preventing of these failures altogether. This is a proactive strategy that helps in extending the service life of wind turbines but also enhances their overall efficiency, making them more sustainable and economically viable option in the long run. Preventive measures in the circular economy of wind turbines involve a multifaceted approach that includes regular inspections, predictive maintenance, and the use of advanced technologies to monitor turbines. Regular inspection allow for earlier detection of potential issues, enabling timely interventions to prevent minor problems from escalating into major failures. Predictive maintenance powered by artificial intelligence and machine learning algorithms emphasizes and it uses the historical data and real-time sensor data to perform matrices that are further used for the detection of the failure. This allows for the preventive actions to be taken. Employing smart sensors and IoT devices on the wind turbine enables continuous monitoring of various parameters such as vibrational levels, temperatures, etc. And we are able to schedule our maintenance by identifying the areas of improvement, etc. Additionally, adopting a holistic view of the turbine's environment, including weather conditions, local geography, and surrounding infrastructures, can inform preventive strategies. Understanding how external factors interact with the turbines can lead to adjustment in installation, operation, and maintenance protocols to mitigate these risks in the long term. This figure shows a detailed wind farm life cycle. The plant is built and operated for a certain period of time. Then decisions are made to either decommission or repurpose the components. The most cost-effective method is life cycle extension that prolongs the operational time of the plants. Among the factors influencing the circular economy of wind turbines energy, we shall focus on life cycle management. Despite being similar in nature, both onshore and offshore turbines use a similar type of technologies. The geography, scale, and environmental factors can play a significant role in impacting the performance of the installed turbines. They show distinguished scope of lengths for circular economy because the operational conditions are different than in the terms of circular economy. The impact of these technologies is also very much different from each other. The onshore and offshore wind turbines show remarkable differences when it comes to the long-term cost-benefit analysis. It appears that the cost to the benefit ratio initially is small in between these two technologies and it grows over the period of time. These challenges are the accessibility, weather conditions, infrastructure, safety equipment, and personal training. The comparison highlights the unique set of challenges faced in the safety inspections of the offshore wind turbines compared to their onshore counterparts. Offshore inspections require not only specialized equipment and training, but also contingency plans for emergencies at sea, given the remote locations and harsh marine conditions. As compared to the manual systems, the autonomous system is fully automated and it can operate uh, using the same technologies for both onshore and offshore. For the life cycle extension, which is a major part of circular economy, we have identified two areas of research which can add the value. These are the fault diagnostics using UAV robotics and power forecasting for the wind energy to schedule the repair maintenance that has been highlighted for the inspection systems. Wind power industry is huge. It is indeed an economy of scales. If we just focus on the wind turbine blade fault detection, Europe wind turbine blade market was valued at around $7.2 billion in 2023, and it's anticipated to grow rapidly at 12.5% over the years from 2024 to 2032. In EU, 3 to 5 megawatt turbine blades market is predicted to observe around 15.3% growth in 2032. 61 to 90 meter wind turbine blades market is anticipated to surpass $2.1 billion by 2032, owing the increased production a large blade coupled with development of modularized and standard turbine components. This shows that the inspection systems which are using the drones, although they come with an initial cost, they can outweigh the cost benefit in the long term. And since there are larger and larger turbines being manufactured, these type of technologies can assist in the inspection very effectively. To further understand the scaling impact of UV inspection technology, we look into the decommissioning blade mass trends. The stats show that up to 64,000 tons per year decommissioned blade mass will be generated per year by 2030. By introduction of faults on blades and timely repairs, we can save huge quantities of waste entering the decomposition stage and avoid tragic failures of operational wind turbines. Forecasting and fault detection technologies have emerged as key improvements for enhancing the reliability and safety of the wind turbine blades and key components. These advancements leverage machine learning, signal processing, and statistical methods to predict potential failures and optimize maintenance scheduling. Here are the list of pros and cons of using each technology. Fault detection in wind turbine blades using multiple channel CNNs offer a highly accurate method for identifying defects and anomalies in the blade surfaces and structures. Similarly, combining PCA principle component analysis with wavelet transform, etc., enables the detection of multiple faults in wind turbine blades and gearboxes. They offer a comprehensive diagnostic approach that leverages transfer learning and convolutional autoencoders for fault diagnostics in wind turbines, allows for utilization of limited data sets effectively, improving the accuracy of the fault predictions. By focusing on wind turbine blades, bearing parameters, and other crucial components, we can reduce failure, downtime, and by proactively addressing issues, can extend operational life of these turbines. Deep learning models can significantly improve the forecasting and inspection of the wind turbines. In this slide, you can see for the segmentation of the fault area after identification, we can use an extended unit architecture. The segmentation of fault area can be done here. This shows a complete encoder-decoder framework architecture. This architecture allows for precise fault area localization that allows for the quick fixing of the defects. In this architecture, an input is encoded for the segmentation, and then the marks are applied, and the decoder encompasses all those areas which are included in the fault and excludes the area which are not to be repaired. Similarly, the blades and the most wind turbines parts are cylindrical in shape to allow for 3D sensors, ultrasound imaging, and sonars for undersurface crack detection of the blades and the other parts. this architecture can be used. This architecture provides a complete 3D segmentation. This model is very effective for crack growth rate prediction and hence allows for scheduling before failure of the parts. Similarly, this encoder-decoder network is a shared backbone architecture where single encoder is used with feature pyramid network for multitask segmentation of lane and drivable area segmentation. This architecture is lightweight and shows excellent accuracy with least number of parameters, which will allow for real-time inspection and processing of less costly hardware. Similar deep learning techniques which we have briefly examined right now that include the CNN architectures, the encoder decoder frameworks, shared backbone architectures, etc. can be used using the encoders based on DenseNet, ResNet, YOLOP, etc. where the feature forwarding and enhancement particularly increases the efficiency. We devise a single we at the end would like to prefer a single encoder based architecture for sensor fusion of camera, lidar, ultrasound, etc. to make our architecture lightweight and able to perform real-time analysis of the defects on the wind turbines. Now we want to further expand our problem and understand the scale of utility of the drones for the inspection system. The wind turbine blades are huge. Usually they are up to 100 meter in length, and the height of each turbine can be from anywhere between 60 to 120 meter. And the curvature of the parts makes it very difficult for visually inspect the defects. So that is why we were talking about the 3D architectures. And standing still of a turbine is not possible because due to the movement of the blades, it's always a dynamic system. The solution can be the utility of drone-based intelligence platform to remotely identify these defects. In the data, we can see that there are different types of defects which can occur on a wind turbine blade. These can be longitudinal cracks, edge cracks, the 45-degree cracks, surface stripping, etc. And then there are certain defects which are caused by the leading edge erosion, etc. When the particles hit the surface of the blade, they chip away some of the area. So this is also caused by the pollution or the impact by the birds, etc. In this slide, we can get a complete picture of the project which we are talking about here. We have an offshore system which is probably expanded into the more than 10-15 kilometers square of area. Then our drone should be able to map this area. On the second step, after the mapping, then we identify and detect the defects on the surface of the blades. These defects can be processed into different types of categories, and the testing should be done on an architecture. These architectures are given here, in which you can see an architecture which is based on SPP and the DenseNet encoder. The SPP is serial pyramid pooling that is used to enhance the feature forwarding in the network, that is also incorporated with the inception systems. In these inception systems are able to identify the a difference between the very minute details within the image data, and using this type of architecture we are able to not only early detect this defect in the turbine blade, but due to the utility of the drone based system, it is a non-intrusive inspection system, and the fault localization can be done, and the mapping of that can be fed back into the system. And after the fault detection, we can see that this type of inspection system is very cost effective. It is also very time saving. The human safety factor of this system is very high, and sustainable wind turbine operations are able to be carried out due to these type of non-intrusive inspection systems. The technical challenges within this system is come from the safe trajectory planning of UAV in the dynamic environment because of the moving parts of the blades, etc., wind and uncertainties in the motion of the drones. Then it should be able to safely draw the trajectory between the in between the environment from source to the destination. And the data acquisition through sensors is also very key component, because due to the quality of the data we can make informative decision, and real-time data processing should be enabled because of the lightweight architecture it can be done. Due to the limited capacity of the drones, these considerations should be made very carefully. From the engineering point of view, this fault detection can be classified into two different dimensions. One dimension comes from the deep learning, and the other dimension comes from the classical control and electronics. To perform this task, we can utilize different type of UV drones and robotics. It will depend upon the capacity, and the drone should be able to handle the weight of the sensor. It should be able to stably acquire the data and have enough processing power and withstand high distortion of turbine and the moving parts. Environmental factors such as dust pollution, mechanical stress, and fatigue cause these defects. Dust pollution can lead to erosion of the blade surface, gradually wearing away the protective coating and exposing the underlying material for further damage. Mechanical stress, including the impact of debris of foreign objects, can cause physical damage such as cracks, dents, or delamination of the composite material used in the blade construction. Fatigue induced by the repetitive cycle loading of the blades during the operation can result in the initiation and propagation of micro cracks, eventually leading to structural failure. These faults necessitate regular inspection and maintenance to ensure the continued safe and efficient operation of the wind turbines. In context of turbine blade defect classification, a common challenge faced is the presence of the classical imbalance in datasets, characterized by the lower resolution of images and less variance in pixel values across the dataset. This scenario complicates the task of accurately identifying these defects, as they are very diverse and the richness of data requires for the effective machine learning models are lacking. To address this issue, an effective approach is to improvise the dataset quality by augmenting it with more data. This can include the capture of additional images under various lighting condition, angles, and resolutions to increase the dataset diversity and robustness. Furthermore, segmentation and annotation of the data becomes crucial steps in preparing the dataset for model training. Segmentation divides the images into regions that correspond to different classes: healthy blade, defective blade, etc. While annotation assigns labels to the segments provides clear guidance for the model on what to learn, enhancing both the quality and quantity and quality of the datasets through careful segmentation and annotation. It is essential for developing models that can accurately classify turbine blade defects, thus ensuring the reliability and longevity of the wind turbines. Here, the deep learning model is shown, which has an inception and ResNet architecture embedded within UAV is for inspection purposes. It represents a cutting-edge approach to enhance the efficiency and accuracy of the structural assessment. This model can be built upon the requirements which were discussed earlier. The model leverages the power of the deep neural network to analyze complex visual data acquired by UAVs and also facilitates the detection and classification of the defects, cracks, or other anomalies in structures such as building, bridges, etc. Uh, as shown in the figure above, an inception embedded deep learning inception architecture known for its inception modules that combines convolution with the different kernel sizes in parallel is particularly adaptive at handling high resolution images, typically of those captured by UAVs. Its ability to capture multi-scale feature makes it highly effective for tasks such as crack detection, where the appearance of the defects can vary significantly depend upon its size, of its orientation, and the lightning condition during the UAV operation. Recent studies have demonstrated the effectiveness of these models in various inspection scenarios, including structural cracks detection, etc. In concrete, experiments have shown that the deep learning models such as Inception and ResNet can achieve high accuracy rates in detecting cracks and other anomalies, outperforming traditional image processing techniques. The inclusion of techniques such as batch normalization, architectural variation, etc., in the model design also proving to be very effective for the increased performance. In here, the pilot study on drone operation for wind turbine blade inspection is presented. It shows a promising results for the maintenance operations. We are assuming a very large scale farm, a 14.5 megawatt into 50 turbines with farms spanning an area of 2 kilometers square. The deployment of the 5 drones is done, 4 in operation and 1 as a backup with a dedicated charging station. We are highlighting the strategic approach to leverage the drone technology for fault detection in this pilot program, and we are utilizing an A-stack algorithm for calculating the optimum routing in between those 15 turbines. The path optimization in a large-scale form improvises the cost effectiveness and also helps to eliminate the flight risk. Since the wind farms involve dynamic environment of the wind turbine, hence it is crucial to mitigate the risk by choosing optimum path. A practical automated damage inspection of wind turbines can be seen in Figure A and Figure B, which shows wind turbine detection and blade tip positioning that are an essential part of UAV-based automatic inspection. Because of the dynamics of the tip, the UAV should be able to detect its position and synchronize with the wind speed to effectively capture the data. Few methods adopt LiDAR or utilize ultrasonic sensors for the inspection, but the cost of these systems is very high. On contrary, the vision-based approach for blade tip detection and positioning, etc., is more cost-effective. To precisely do the operation, we first detect each structure of wind turbine by combining CNN-based encoder for blade detection and the shape of the constraints. The pixel coordinated of the blade tips can be extracted and then can be used to solve the navigation problem. For more realistic approaches, the experimental simulation must be conducted to ensure the feasibility of the prevention techniques. The circular economy also takes into account the initial carbon footprint. By reducing the testing cost, we attain positive impact on LOC. Once a fault is located in the wind turbine, we can utilize the information provided by the forecasting methods to schedule the repair process. Here we see a day ahead forecasting that we are able to forecast 12 days ahead with high precision. The repair time must be adjusted where minimum energy is lost due to the downtime. In this study, a federated learning based temporal network is utilized. It provides the data privacy features as well as high accuracy of prediction of wind power. By this time ahead forecast, knowledgeable decisions can be made. UAV path optimization is a critical aspect of mission planning, ensuring safe and efficient flight paths while avoiding collisions and minimizing energy consumptions. The goal is to find the most suitable trajectory that meets the mission requirements, navigates through obstacles, and optimizes for the cost functions. These cost functions can be distance traveled, time spent in the flight, or the fuel efficiency. To dig deep into the target and or the path optimization, we have to draw a mathematical model. The target location is modeled as a point mass moving on the ground where the target states are given by the location of the individual infrastructures. The target location is abstractly represented as a point mass moving on the ground, simplifying the complex geometry of the wind turbines into a single coordinated XY pair. The modeling approach allows for the formulation of the target states that describe the target's position relative to the UAV, facilitating the UAV's navigation and obstacle avoiding tasks. Since the wind farms are usually occupying very large area and the wind turbines placements are not standard, the drone navigation model should be able to navigate through complex environments. As shown in the figure C, uh, the models should be intelligent enough to solve the maze to reach the intended target. Deep learning models with stochastic optimization can provide an in-depth capability for the drones to navigate in the complex operating environment. Now we can quantify the impact of the inspections of wind farms in onshore and offshore settings. The integration of UAV inspection and wind power forecasting plays a crucial role in enhancing the circular economy of wind turbines by promoting sustainability, reducing waste, and extending the operational life of these renewable energy resources. Advanced drone and robotics maintenance strategies coupled with diagnostics and inspection techniques support the certification of wind turbines for extended lifetime, thereby reducing the need for premature replacement and the associated environmental impacts. The use of autonomous drones combined with digital twin modeling can significantly reduce the operational costs associated with manual inspections. This technology enables faster, cheaper, and safer inspections potentially. This graph gives a detailed comparison of materials and utilities in onshore versus offshore wind turbines projects. We see that the offshore wind farms benefit more from UAV-based inspection systems from the absence of physical obstructions and the steadier wind conditions, which contributes to a higher capacity factor expected to reach 60% by 2050 for new projects. Onshore wind farms, on the other hand, despite producing less energy per megawatt, are recognized for their reduced environmental impact, quicker installation times, and lower operational cost. These are also more cost effective and contribute significantly to the job creation and renewable energy sector. This graph shows the impact of fault diagnostics on the performance of the wind turbines plants as a green energy over the extended period of time. We suppose the surface life of a turbine is 30 years. The degradation patterns can be seen here with and without the fault detection systems. A more stable performance over time with small manageable drops extending the turbine's life and maintaining higher accuracy can be seen. This graphical comparison effectively illustrates the significant benefits of the early fault detection and maintaining uh, the longevity and reliability of the wind turbines. To conclude and give the future directions, we can say that the EU's commitment to the circular economy in the wind power is very much evident. EU has made a significant commitment to transitioning towards a circular economy within the wind power sector. This commitment is reflected in the EU's strategic policies and initiative aimed at promoting renewable energy sources, including wind power, as part of its broader strategy to combat climate change and achieve sustainability goals. The circular economy approach emphasizes the reuse, repair, refurbishment, manufacturing and recycling and recovery of resources, aiming to minimize waste and maximizing source efficiency. Within the context of wind power, this means focusing on the entire life cycle of wind turbines from manufacturing to decommissioning and exploring ways to extend their surface life. In here we have shown that the utility of the modern technologies, deep learning techniques, robotics and UV drones, etc. We can extend the lifespan of the existing fleet of the wind turbines in the EU. Uh, Looking ahead, future research and technological advancement will be pivotal in realizing the full potential of the circular economy in wind power. Innovations in wind design, material sciences, and manufacturing processes could lead to more durable and recyclable wind turbine components. Additionally, advancement in data analysis and predictive maintenance technologies could enhance the ability to monitor and manage the health of wind turbines, allowing for more proactive and efficient maintenance practices. Research into new business models and financial mechanism could be facilitated by the adoption of the circular economy principle in the wind power sector, encouraging investment in sustainable practices. As the technology and the knowledge base continues to evolve, so too will be opportunities for creating a more sustainable and resilient wind power reliability.
Thank you so much to all the speakers for their valuable insight and contribution today. I hope this discussion has inspired new ideas and collaborations as we continue working toward a sustainable future through the circular economy. Thank you so much for listening.